Good morning, good afternoon, everybody. Dave Holdorf here with Taco Comfort Solutions, presenting Taco Tuesday today on June 21st. Today is our residential focus on low temperature hydronic applications. So I am happy to see everybody logging in and a bunch of people jumping on board. So I see a couple of familiar names out there, Mr. James and Kerry. So far jumping on board. So glad to see you. And I see a whole bunch of people logging in as we speak. So I do greatly appreciate you all spending Tuesday along with us. Well, actually just me at the moment. John and Rick are at the factory right now where I was supposed to be too, but unfortunately diagnosed as positive. I was feeling horrible yesterday and tested positive today. Feeling a lot better today. Yesterday I was in no way, shape, or form to be able to get out and or even do something online. So, but today, totally different story. But there we go. That's what's going down. So, but I will be able to muscle through this presentation today. So, with that being said, we will get this party started. So, for those of you that may be new to GoToWebinar or not familiar with this this setup here. A couple things I want you to pay attention to on the control panel if you have trouble seeing or hearing me right now. What I want you to do is take a look at that arrow, that orange arrow. If it is pointing to the left, click on it, and you'll be able to get to the different sections of the system where you can get your audio, your sound, and videos to make sure you can see everything going on out there. I do have a couple of handouts out there. We have the takeaways brochure, which is our so to speak, cheat sheet with a bunch of formulas and calculations and things like that that we cover on the residential side. And at the bottom of the screen, you'll see a questions chat area, and that's how you go to communicate with me. So I see Eric Hoffman already jumping in there first saying, and if I can ask everybody real quick, just to make sure it's all working and everybody can hear me, a quick hi, hello, how are you? It would be perfect from everybody out there. We got a ton of people logging in. Just want to make sure everything is working. And I will ask periodically to sit, to even answer a question for me. And it might seem like a simple question, but it also guarantees that we are still connected and I'm not talking to myself here at home. So excellent, Bill and Zach and Rich and Brian, Mike and Corey. Excellent. Thank you so much for logging in and participating with me today for Taco Tuesday. If you are using GoToWebinar on a device, things will look a little bit different. You have to toggle at the bottom of the screen between your audio settings and questions and to see the screen and or the camera today. So that's where you're going to do that if you're watching this on a device today. So before we really start talking about the different applications and start looking at low temperature hydronics, it is all about the heat loss first. And otherwise, we are just guessing on stuff out there. So we need to do our heat loss first. Otherwise, we don't know what we're doing, and we'd have to be guessing on a lot of things out there. So, for example, and I'm not going to go through doing heat loss today. We've done this probably a few other times in Taco Tuesdays and on Taco After Darks. So I'm just going to punch in a couple of numbers that we have on this 10 by 15 room with 9-foot ceilings, 2 exterior walls, and 3 windows, and we find the heat loss of that room at 3,216 BTUs per hour. All right, not a very large room, 150 square feet. All right, and if I remember correctly, the outside design temperature for this structure when we did it was around 0 degrees outside and a 70-degree indoors. So 3,216 BTUs per hour, and if you're curious, the rest of the house comes in at around 39,000 for a total of 43,000 BTUs per hour of the heat loss of the house. I've used this example in this house in many other presentations over the years. So this way we've got some place to start with. So we need to have that starting place before we can figure out how much heating element that we need to put into a space. So how much radiation is needed? 3,216 BTUs per hour. Basically, you go to the charts from the manufacturers, all right, and pay attention to what they've got going on here. So this is a chart coming from SlantFin, and what you're looking at here is a couple of different rows and a couple of different columns, and what you have here is supply water temperature. So when you look across the top of the chart here, these are supply water temperatures that you would be sending out to your fin tube element, all right, and then they give you 2 different rows. where we're looking at 1 gallon a minute and 4 gallons a minute. All right, and which row do you use? Well, it all comes down to the notes that are down below. You take a look at the notes down below, and all the way down here it says use 4 gallons a minute ratings only when flow is known to be equal to or greater than 4 gallons a minute. Otherwise, use the 1 gallon a minute ratings. So we're going to use that 1 gallon a minute ratings, and if we were to use 180-degree water for our application, which is where a lot of fin tube baseboard was originally designed for, was at 180 or higher a lot of times. And here we're going to find out how much we actually need into the space itself. So we can see we'll get 580 BTUs per linear foot of fin tube element running at 180-degree supply water temperature. So when we do that math, we figure out that we need only about 5.5 feet of element. Now, for a lot of you out there, you might not see a 10 by 15 room with 5.5 feet of baseboard in there. What would you typically see in a lot of projects with fin tube element? You know, how much would you see put into this room that was a 10 by 15 room? I know what I see all the time. And also here on the land, yes. 15 or 25 feet, yes. At least a 10-foot wall, Eric, yes. Some people just put baseboard wherever you can. Outside wall with a window, you just fill it, right? Or at least if you did the math, all right, what you'll end up seeing here is 5.5 feet was the calculation. All right, that was the guy back in the office. The job supervisor went and wrote on the stud and said, well, 5.5 feet, I'm not going to do that. We'll put 7 feet, and he'll write 7 foot on the stud. And then the installer comes along and says, well, 7 feet's just not going to look good on this 10-foot wall. We're just going to fill it from corner to corner, right? But we only needed 5.5 feet. So, or you just fill the other outside wall and make it 15 feet, right? So what if it is oversized? All right, what if you do have those 2 outside walls thrown in there? Do we need to run the system at 180 degrees? Definitely not. Let's lower that water temperature and let's go back to those charts again that we saw from Slant Fin, because if we pay attention to what they had in there, they'll also tell us, let's say we had the 10-foot wall installed minimum, right? What water temperature we want to run this to? So when we take a look at those charts, you see over here on the right-hand side, or left-hand side of the column, you see some shaded areas. And the shaded area here was, they shaded that part out of the charts to say, hey, if you are using a modulating condensing boiler, we want to make sure you've got lower water temperatures. All right, and below 140 degrees is when that boiler starts to consider condensing, you know, therefore getting that mod con part of it in there. So you want to get down to that temperature minimum. You can go lower, sure, definitely, right? But make sure we look at doing it that way, and that's what these charts are going to show us. So let's say we had the 10 feet in there, and if we had 10 feet, let's take a look at the heat loss, 3,216. We have 10 feet of element installed, and we only needed 5.5. So if you take 3,216 divided by 10 feet, you'll find that we need 321 BTUs per foot. All right, and that actually falls in really close to the chart here at 321. So we can see that we would need 140-degree supply, which means we would have 120-degree return, all right, is our goal. So therefore having that 20-degree delta T on there, and as the cooler temperatures prevail on the return side of the boiler, the better chances of this boiler going to condense. All right, I hope that makes sense, everybody, so far. Just taking a look at that as we go through an existing system. Now, if you were designing, all right, now, yes, I saw a couple answers come in here saying, hey, 25 feet. You know, if you filled both walls, all right, just do the exact same math again, 3,216 divided by 25. All right, now we probably might fall off the chart here, so they're probably not going to see a lot of heat output once you get below that 110 degrees for your fin tube baseboard. So, so just be careful how low you go with the system as that. Now, if you really want to start going low, there's a lot of different applications, a lot of different manufacturers out there making different types of fin tube element. So this one here I thought was pretty unique to show off, and it's called Heating Edge. And Heating Edge actually has 2 supply pipes, or 1 supply, 1 return, depends on how you pipe it up, and they have a very high output temperature if you're running it at that 180 degrees. So we take a look at their charts, and I just grabbed a couple, I just grabbed a part of it so you could see everything. But what you see here is, how are you piping? Are you doing two supplies in parallel? You do two supplies in parallel, and for example, you start looking at these numbers, that's the highest heat output that you're going to get. But if you were to do a top supply, bottom return, or a bottom supply, top return, all right, we're getting some pretty good BTUs coming out of here. So again, let's take our heat loss of the project at 3216, and now we're going to do a new install on here. So we're not working with what's there. Let's do a new install. Let's maybe replace the baseboard that's there. Let's put this in so we can operate on as low a temperature as possible. So we'll do the top supply, bottom return. And let's say we'll grab that 226 BTUs per linear foot, and we come in at 14.2 feet of element. So running at 120 degrees. These charts are a little bit different. All right, this manufacturer is listing the water temperature as your average water temperature. As you can see right here at the top, is going to be your average water temperature. So we're looking at 120 degree supply water temperature. So getting a little bit lower than your fin tube, your standard single fins out of the system itself at 140. Now we've got 120 degree supply. So just different ways to look at it. Pay attention to those charts that you'll see out there, and we can see a whole bunch of numbers that we can work with that's going to get us what we're looking for in our systems. All right, now, yes, cast iron baseboard. Yes, there's a lot of it still out there. There are tons of people out there that have it, they love it, and they never want to see it go away. And there's a bunch of people out there that have it and want to see it go away. And it's because, these things give off such a high heat output per linear foot. Nice big chunk of cast iron. You've got some fins on the back side of it. So you've got two different types of heat that you're radiating into the room itself. You're going to have that radiant energy from the cast iron, but you'll also get that convective current too. Therefore, the slot at the bottom and the slot at the tops to get that convective current to come into the space. Whereas when you look at any of the fin tubes that we looked at earlier, they're all looking at strictly convective heat transfer going on into the space itself. So this is a nice system. The downside to it when people have it in their home is because it's always been hooked up to 180 degrees and these things get darn hot. So lowering that temperature is never ever a bad idea, but of course we have to take a look at the numbers. So here we take a look at the numbers from Base Ray, this from Burnham. And Burnham had some numbers on here and they went as low as 150 degrees. Now, this is all I was able to find on their website. They may have something elsewhere where you can find lower BTU output per linear foot. So at least we can run it at a lower temperature of 140 degrees. And again, this is going to be the supply water temperature. Always pay attention to that. Each manufacturer is going to be a little bit different. You want to pay attention to whether it's going to be the average or the supply listed. All right, and that's what they're showing here. So we have, say, that 10 feet installed on that one wall, 3216 divided by 10, hey, 321 BTUs per foot. And yeah, their charts are showing 340, so let's just call it 145 would be my supply. Not exactly 150 that you need. You get a little bit more, so 145 or so would be more than enough in this space itself. So, so still working with that cast iron baseboard and getting to operate at lower temperatures is one, going to add a level of comfort into the space it's two, and also get that new boiler to operate where the homeowners are expecting it to, right? So we took out that big old cast iron boiler and put that nice wall hung on the wall. Let's make sure it's going to see those fuel savings that the homeowners are looking for. So get that temperature as low as you can. Now, we could jump into panel heaters. And I do have a quick question before we keep on going. I notice that I'm going really fast. I need to slow down just a hair. All right. Yes, I'm sitting here by myself right now. But how is the pace? Is there any questions on what I've covered up to this point so far? I went kind of fast. I want to make sure that I'm getting all the points that everybody's looking for. How's the pace so far? All good? All right, Lauren and Kerry. All right, going well, Brian. Thank you so much. Just want to make sure that I'm not going fast. I am going a little fast, but I should be slowing down just a little bit. And we've got a couple other applications to talk about here, and panel heaters are starting to gain some popularity here, I would say, mostly in this low temperature world, as we say, looking at this stuff now, right? So panel heaters are looking at now really taking a look like a cast iron type of radiator. We still have, and some of these will have convective and some of them won't. Depends on the manufacturer. They will have that fins on the back side of it to get you that heat transfer, that convective heat transfer, but then they also have that steel portion. So it's not cast iron, so to speak, but now you get a lot of custom configurations that they can make out of these steel panels themselves. And we have some of them throughout the factory at Taco. So if you've ever been to any of the training rooms at Taco, you'll see them along the outside walls where we had some custom panels made for us locally. And the one that we do have at our place is panel baseboard. And for example, you take a look at this company, this manufacturer, they have a 2 rows, 3 rows, or 4 rows of the fins of the elements themselves, and then they have it with fins. And so there's this one chart that you'll find online, which is talking about their BTU output at 180 degrees. All right. Now, give them a call and you will find the lower temperature outputs. All right. So I do have, I did talk to for a company Runtal here. They were based in Connecticut, and they were able to get me their lower temperature heat output charts. I couldn't find it right away on the website, so they had emailed me. And if you're looking for it, let me know. I can easily send those charts out, but I'm sure if you were to give them a call, they can get it for you too. So, so if you were to use it at 180 degrees, all you need is 5.2 feet in this application for the 2-row section, for the 2 rows. So very similar to your fin tube element. All right, so going back to a regular fin tube element here, it matches up rather closely to the heat output that you had before. But I got this chart from Runtal, and here, if you take a look at the tubes, all right, the VLX 1414, all right, and let's say we wanted to fill that 10-foot wall, again, like we had before, we're looking at 320 BTUs per linear foot is what we need for an output. So just peruse the chart and find where that 320 is going to get closest to you, right? So not exactly 130, not exactly 140, right in the middle. All right, and again, this is average water temperature. All right, so if we were to use the 140 chart, we'll get 150 supply. We're going to get 349 BTUs per linear foot. All right, coming out of there. So yeah, we could probably drop it just a hair again, like that 145, like I was showing earlier today. So extrapolate those two numbers that you want to get for your heat output out of here. Now, if you were looking at, say, panel rads, and you wanted to go a little bit taller instead of lengthwise in there, they have lots of different configurations there too. And again, these are showing you the heat output at 180 degree charts. And if we were to pull up the 4949, which looks great underneath some windows in some applications in some houses, fit it underneath that 4-foot window. All right, you'll get all the BTUs that you're looking for. Now, if we were looking at lower water temperatures, same chart again. They do have now the 7-tube high. All right, so divide that by 4. We're going to get 804 BTUs per foot. And we can see that we'll operate at around 145 degree water, right there in the middle between the two of them. So, so use those charts from the different manufacturers. They're going to give you all the information that you need in order to operate these things at a much lower water temperature. Now, what about radiant floor heating? All right, radiant floor heating we always consider to be the ultimate in low temperature low temperature hydronics. Excuse me, I am a little dry and a little dehydrated. So the last couple of days I've sucked down quite a bit of water. Anyways, so radiant floor heating, as we go through and start looking at all the different radiation that we've talked about so far, each one, the mass starts to get a little bit bigger, all right? And as the mass gets bigger and bigger, we can actually start lowering that water temperature. So now you've got something that is the entire room, the entire floor that is going to operate as the heat emitter itself, so we can really start lowering the water temperature. And when we start talking about radiant floor heating, we always like to start talking about it in BTUs per square foot. All right, so BTUs per square foot is how we discuss radiant floor heating. It is not per foot of pipe itself. And my previous life before I came on board at Takeo, I worked doing radiant floor heating designs, tech support, troubleshooting job sites, you name it, I was doing it with radiant floor heating. And a lot of times we would get people to hold up that piece of pipe and say, how many BTUs per foot am I going to get out of this? And I said, it's not the pipe that heats the room. It's the entire floor assembly is what heats your space itself. The entire floor must heat up, and then we'll get BTUs delivered into the space. And we always like to talk about it in BTUs per square. So how much can I get out of per square foot, right? We have the heat loss of our room at 3216. Divide that by 150 square feet, and we'll have 21 BTUs per square. All right, so that's the number we need to work with. And this is available floor area. If this happens to be, say, a kitchen, or it happens to be a bathroom where we do have vanity, or say a tub, or spaces that where we do not put the tubing. And if we were to put tubing underneath cabinetry, say in a kitchen, it does not add to the heat delivery into the space itself. That's lost floor area. So it has to be the available floor area. All right, so change the square footage, take out those cabinets. If it's along the 10-foot wall and it's 2 foot deep, drop out 20 square. All right, you got to drop that that calculation out of there. So, and that's where kitchens and bathrooms usually becomes a little bit more challenging to try to heat because of the loss of area there. All right, so at 21 BTUs per square foot, now we go ahead to the different manufacturers, and every manufacturer is going to have BTU outputs that you can find. So this one happens to be coming from Uponor. And this is showing us what water temperature we need based upon a 4-inch concrete slab, and the tubing is set at a 9 inches on center. All right, so pay attention to that on the top of the screen where it's a 9-inch on center. And as I said before, it's not about how much tubing is in the space itself, all right, in order to heat a space. Spacing of the tubing itself will just lower your water temperature. It's not about how many BTUs per linear foot of pipe do I get. It's all about that square footage. So what we look at here is a BTUs per square foot on the left-hand side of this chart. All right, across the bottom here is going to be your supply water temperature, and you have it set up as a 10-degree delta T or a 20-degree delta T, your choice in your designs. And then the diagonal lines are the floor covering R value. What is the finished floor on top of the concrete? What is the R value of that finished floor material? So if you're not sure, I believe they have a chart in their book also in Uponor in what they call their Complete Design Assistance Manual. Big book has a lot of information in there. You'll be able to find those different floor covering R values. That is everything put on top of the concrete and added up as you go through. So the way this works, all right, is you take your 21 BTUs per square foot and draw a line until you get to the diagonal line that you are trying to match up to. So for this application, I was going to go with a engineered wood floor that would sit right on top of the plywood deck. And a 3/4 inch wood floor is going to have an R value of around 0.7, 0.8. All right, so I went in between. I'm sorry, this one's no, this one's a 1.2. I'm sorry. Whatever I was choosing here, let's say it was going to be a thin carpet going down on top. So you had an R value of 1.2, or you had a plywood deck and then the hardwood floor getting on there too. So maybe a traditional nail down system. So you might have an R value around 1.2. All right, so we have that diagonal, and where the two of them meet up, we drop down, and we can see that if we ran our radiant floor on a 10-degree differential, we are looking at sending out 110-degree supply water temperature to this concrete slab. If you're looking at a 20-degree delta, it would be 115. Now, radiant floors, we do like to typically residentially send out a 10-degree delta. It gives a more even surface temperature in the space itself. So that's where I like to run my radiant floors as around a 10-degree delta like that. So we're looking at 110 degrees with a 100-degree return. So our boiler is going to love that. Going to love that nice cool water temperature and help that boiler condense as much as possible. Now, let's say we had a different application, because every radiant system is going to have a totally different application. And let's say instead of a slab, a 4-inch concrete slab, we have an 1.5 inch poured floor, all right, like a mud bed, or not necessarily self-leveling, but you've got some gypsum-based systems that are pumped into the house, and they are typically an 1.5 inch thick, all right. And they don't, and I don't say that you're going to see that as a self-leveling. A lot of people assume it is. It definitely is not. What you do is when they pour it in the house, they do it in 2 pours at 3/4 inches, and they usually use a 2x4 on edge to get the levels on where they need to be. So now this one we're doing, say, a 12-inch on center spacing. So as we take a look at the charts the exact same way, paying attention to the top on which application you're doing. And so, nope, I see a question that came in from David, and he was asking, what is the typical R value for the 4-inch concrete slab? Now, we don't have to worry about the R value of the slab itself because the concrete is our heat emitter. All right, the concrete is our heat emitter. We're heating up all of that concrete, which then has to push through the floor covering R value that's on top of it. Okay. When we do our heat loss in a radiant application, we do need to know what is the R value on top, but also what is the R value below. And it is always suggested, if you're not sure what to put below a radiant slab, at least 5 times what's on top is your minimum R value, is a suggestion. You could always go more. The more R value, the better, to help that heat transfer and to control the system a little bit better. Kerry, I will get to that question just in a second. He was asking about what are the grooved plywoods for tubing? Should they have a similar table? Most definitely, and I actually do have that one showing up here in a couple of minutes. So, 1.5 inch poured floor. All right. We say again, we're going to take our 21 BTUs per square, and this one's going to do the plywood deck, say with a hardwood floor again, and we'll have an R value of say 1.2. So where the 2 arrows line up, we drop down and we're looking at just over 130 degrees with a 10-degree delta. All right, so 12 inches on center. Yes, the wider spacing does make it, you increase your water temperature going out there. And being that we don't have the same mass as that 4-inch slab, we need to raise that water temperature just a little bit more also. So, so that's what we look at when we start paying attention to our radiant floors. Now, if we look at underfloor applications, and again, I'm using these charts coming out of the Uponor book. All right, and now they have their joist track, which is a metal plate that gets screwed up to the underside of the floor, and then the pipe gets snapped into that, and then we insulate behind that. Is the application that I'm looking at. So almost identical to what we've been looking at, as in, look at your BTUs per square foot along the left-hand side. Now you have your R values on the diagonals, but what we also need to pay attention to, all right, is this little note right there. The temperature chart has already factored in the R value for 3/4 inch plywood subfloor. So as we are doing this from below the floor, every room above is going to have a plywood deck, all right, and it's probably going to be a 3/4 inch. So then we just go and put the our hardwood floor right on top of that. So therefore, we don't need to be at the same 1.2. We just need to be what the finished floor covering of the wood floor is going to be, of the 3/4 inch strip oak flooring, right? So that would be around a 0.7. So where the 2 lines meet up, then we drop down and we see from below the floor, we're looking at 110 degrees. And this kind of freaks out a lot of people because they think, oh my, how am I using a lower water temperature from below the floor compared to the gypsum system that was done on top of the floor? Well, we had the same R value thrown on top of it, okay? This one, is the joist track is meant to simulate mass, to really transfer and pull that heat out of the pipe itself and put it into the floor area. All right, so it's not a huge difference. And as far as the boiler is concerned, the boiler is really happy to see those, either one of these applications. All right. When you look at designing a home with radiant floor heating, don't change the house to fit the radiant, change the radiant to fit the house. So if you were to look at doing that 1.5-inch poured floor, you need to make sure the house can handle that extra weight, that extra load, and of course the extra height thrown in. All right, we're adding that 1.5 inch more of that floor. You got to make sure the load, that extra weight can be handled, or go from below the floor. You know, we're looking at different ways and different applications. To the end result is that we're still putting radiant heating into the space itself. Cost-wise might be similar. If you were already doing the gypsum in there for sound deadening and for strength of the floors themselves, awesome. Put the tubing in that. But just don't go adding the gyp in there because you want a radiant. I hope that makes sense for everybody out there. So question from Lauren, do you folks in the Northeast really set your room set points to 65 degrees? As a guy with forced air heating, that seems low to me. Oh, correct. Totally. All right. These are just their charts that they have based upon a 65-degree room set point temperature. That doesn't mean the thermostat is set for 65. All right. That's what their design was for. All right. If you want it to be 70 in your room, you set the thermostat to 70. All right. It's amazing in a room with radiant floor heating, all right, that you do feel comfortable at lower air temperature settings. So whenever I would go and set up any systems out there, I would try to put some blue painter's tape over the digital display of the thermostats if it was an easy enough thermostat to use, as in, and just show the up and down arrows if that's all they needed, and said, change the numbers until you feel comfortable, but don't pay attention to what the actual number is. You'll be surprised on what that number is going to be. But it is also a mental thing. All right, people don't know if they're warm or cold until the thermostat tells them so. All right, my wife used to do it to me all the time. She would walk into the room, we'd be sitting there, I'm sitting there watching TV, and she's like, oh, it's cold in here. And she'd say, well, what temperature is it? And I'd lean over and look at the thermostat and say, oh, 70 degrees. And like that, she was warm. She's like, oh, okay. It's amazing what that number does for you. All right, whether or not people feel cold or not, that the thermostat tells them they're warm or cold. Another application, another job site I remember going to, and the whole, I had suggested to put the blue tape on there, and the homeowner said, nope, I'm going to turn it to 72. Okay, all right. And as a week goes by, he goes, this system is crazy. It's not working right. You need to come over here and take a look at it. It's way too hot in here. Something's not correct. So I get there, and the thermostat is still set for 72 degrees. And, of course, you got to look downstairs and pay attention to mechanics and making sure everything's opening and closing and turning on and off and whatnot, and everything is doing what it's supposed to be doing. And he said, I said, you need to lower the thermostat. Just because you used to have your old system set for 72 doesn't mean you need this one set for 72. All right, it's just a number. It's a different heating application. So lower it. And he's like, yeah, I don't think that's going to work. All right. So I said, well, give it a couple of days. All right, I'm going to lower it down here. I'm going to put it to 69 degrees. And I'm going to come back in 3 to 4 days, or give me a call if that seems to make it work. And so as those 3 or 4 days goes by, I was nearby. I stopped in to see how everything was doing. And the homeowner says, yeah, that worked. And I'm like, well, simple phone call would have done. And he's like, yeah, but I wanted to apologize face to face with you. I'm like, no, really. The phone call would have been just fine. But anyways, it was really interesting that, just you don't necessarily have to pay attention to the number. The number is just a range. It's just something to work with in your own home. Okay. Yes, Heidi's saying the heating system doesn't need to be a heat source like a fire. Lower temp is healthier. Doesn't dry out your skin or make you as thirsty. Definitely, right? I mean, and depending on how we're heating, I mean, that's why we try to design a lot of these projects out there with hydronics, say over forced air with a furnace that's is drying out the air, because then we got to go ahead and put moisture back in, right? So slow and gentle. As we start thinking about hydronics and start doing low temperature in here, all right, one of the things that we've talked about is BTUs per hour. All right, that 3,216 BTUs per hour. Do we want to put all those BTUs in there in 10 minutes, or do we want to do it in, say, 1 hour? So we think about that for a second. Think about that. All right, the BTUs per hour, right? It's how much heat is lost in 1 hour, and I need to replace it. Let's not do it in 10 minutes. You do that in 10 minutes, the temperature swings are all over the place. The room gets warm, it gets cold, it gets warm, it gets cold, right? If we slowly put the BTUs into that space, we're not using any more energy. It's the same amount of BTUs that are going in there. We're just going to do it over a longer period of time when we do it with low temperature hydronics. It just takes longer. So that's important to pay attention to. This is also important to describe to your homeowners how the system is going to operate. If they have never lived with low temperature hydronics before, we need to explain to them what is going to happen, all right? Which means a couple of things. Things won't feel as hot as they were before, meaning the heat emitters. Case in point, my in-laws, all right? My in-laws had a 47-year-old boiler in the house with fin tube baseboard and one zone colonial in the house. So we took out the old boiler, put in the new boiler in, nice new wall hung condensing boiler, hooked up the outdoor sensor, programmed the curve. It was way over radiated. All right, we had way too much fin tube baseboard in the house, so I did the heat loss on the place, and then I saw how much element was there, and the hottest I needed to make this house run was 150 degrees, 150 on a 14-degree design temperature Fahrenheit outside here in, where I live on Long Island. So modulating boiler, obviously modulating circulators are going in there, right? So I'm modulating everything that I possibly can. And, you know, we did the work in the summer, didn't wait for stuff to fail. We did it in the summertime, so we were safe. And as the first cold snap came along, the heat had already been on, but the first cold snap comes along, say in November, and I was on the road. So I think I went to Baltimore for a few days, and I knew my wife was coming over here. We lived about 30 minutes away at the time, and I knew my wife was coming over here with the family. So I said, oh, let me just call over there. Of course, she didn't answer the phone because she left it out in the car. So I called the house line here, and my mother-in-law gets on the phone, and I, you know, just being cordial, of course. And I said, oh, by the way, how's the heat doing? And she says to me, oh, I don't think it's working. Now, I just got down to Baltimore, and I'm going to be there for the next 3 or 4 days. In the next 2.5 seconds, I'm just imagining on who I can call, which contractor can I get over to take a look at the house, what's happening here, what's going down. And I said, whoa, all right, hang on a second. So, Mom, what's the temperature in the house? Well, she says it was 69 degrees. Okay, what's the thermostat set for? And she says, well, it's set for 69 degrees. And if you do the math, that's working. All right. And I said to her, I said, well, what do you mean? Why did you say you don't think it's working? And she said, well, I don't hear it anymore. Meaning the high temperature fin tube baseboard running 185 degrees, tick, 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 right? And it's sliding across the hangers of the element and the pump turning on and whooshing through. Yes, there was an old B&G 100 in there, right? So now I swapped it out, running low temperature. And at this point, it was probably running around 130 degrees. Yes, Lauren, I had Delta T circulator in my house. I had one of the first Delta Ts that we had made. If you all remember the Bumblebee out there, worked great, working awesome in the house, right? So she was just not sure that it was working. All right, she was used to all those noises, and I never explained any of that to them. I just said, oh, we're putting in a new boiler and it's going to be a lot more efficient, you know, and we'll see the fuel bills drop because it was a smaller boiler, all this other stuff in there. So point of the story is, I know what story went a little bit longer. Tell your customers beforehand, give them the explanation, because when you tell them afterwards, it's an excuse. All right, let them know what's going down because as we're doing low temperature hydronics. Okay, so let's also take a look at radiant floor heating. Sorry, let me just jump back into the presentation here. I can tell you stories all day long. As we start looking at a radiant floor system from below in that joist cavity again, but we're eliminating the plates. So we don't have the metal plates going in. Now we do a 2-inch air pocket from below and insulate underneath that. Again, we use the exact same charts as we've been using, not the same charts, but the same idea. Take a look at the 21 BTUs per square. All right, again, this has the same 3/4 inch plywood subfloor put in there, where the two of them line up, and we're looking at about just over 155 degree water. All right, so we had a big difference in water temperature with and without plates. Are we condensing as much as we can here? Probably not. Probably not. Right? So if you want to take advantage of the modulating boiler, the lower the temperature, the better. As you start working through and setting up your different designs out there when it comes to low temp hydronics. All right, so like I said, lower that water temperature, get it as low as possible. We way over radiate a lot of existing homes, so we can make it all work by lowering that water temperature. And yes, it's going to mean doing the math, all right? And it may mean doing the math twice, as in do the heat loss on the house, then go back and find out how much element is in there, and then see what water temperature you need from there. So we want to get that temperature as low as possible. Set up the outdoor reset curve, all right? And unfortunately, I have learned this statistic from a lot of the different boiler manufacturers. I know them all. I know a lot of the people out there. I go to the trade shows and I see them all, and we do training classes together. And the alarming statistic that's out there is 60%, 60% of the wall hung modulating condensing boilers are not modulating and not condensing, meaning they do not have the outdoor sensor set up on there, or the outdoor reset curve was never programmed. It is sitting there at 180 degrees all the time, and maybe drops down to 140. All right, so that window of modulation between 180 on a design day and maybe the low end of 140, the boiler never really sees condensing except when it's like 65 degrees outside. Okay, so set up the outdoor reset curve, put the outdoor sensor out there, explain to your customers what we're doing. And I know why a lot of sensors are not hooked up, because of the explanation / excuse. And also the other half of the story is homeowners have been told for the last 20, 30 years how to save fuel. How has a lot of homeowners figured they could save fuel? What's the one way? And we've seen it in a lot of brochures, especially from the government, right? How are you going to drop your oil bill or your gas bill in your house, right? And there it is from Rich, definitely setback, right? We're going to turn those thermostats down, all right? Turn them off when you're not using them, or lower that temperature setting in the house itself when you're not there. Say when you go to leave for work during the day, or when you go to bed at night. A lot of people do like a cooler in their house, right? And what ends up happening is, oh, well, I've been setting it back, 10 degrees, for the last 15 years. And actually, their amount of fuel savings doesn't seem all that high. All right. If anything, it's actually the enemy, and their fuel bill may go up because it takes a lot more energy to bring everything back up to temperature again. And it's not just the air, right? It's the element itself. It's the walls. It's all the furniture in the house. Everything has to warm back up again. Now, when is a boiler most efficient? Yes, when it's off. All right. So I do agree on setback. You can do setback. All right. And I do it here in my own house. However, don't go as deep. Don't need to do a 10-degree drop. All right. Maybe 3, 4 degrees. I do a 3-degree temp drop at night on my radiant floor system in the house with the slab. What happens is it takes a little while for it to get back up to temperature in the mornings. All right. I have it turn on around 6 o'clock, and usually by 9 is when we're back up to temperature at 70 degrees. All right. And that's where it feels comfortable for us in the house. But I do have it go down to 67, and it stays off the entire night. The entire night that system stays off because I have all that stored energy in the slab. And so it takes a while for it. But when you stop and think about what's happening between 6 and 9 in the morning, the entire house is waking up. Everybody's getting ready for school, for work, this, that, everything's moving around. All right. Now my wife does stay home. So by the time everybody leaves, now it's nice and comfortable, and she goes and has her breakfast and stuff. Right. So, so make sure, again, homeowners know what's going on. Set up the outdoor reset curve in that boiler itself. All right, read the factory manual that comes with it on how to do it. All right, don't be afraid of it. And that sensor must go on the north side of the house away from any venting, meaning the boiler vent, the dryer vent, anything that's going to throw off that temperature setting. All right, that sensor itself. So make sure it's going on the north side. The sun is not hitting it. It's in the shade itself. It doesn't get buried below the snow line, right? We don't want that either because snow becomes an insulator. So we want to make sure it's up nice and high, and we're not near anything that's going to make it warmer. All right, so get that sensor outside. All right, modulate, 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 right? I like to say modulate the world. All right, so yes, if we've got the boiler modulating and you've got modulating circulators out there, all right, you put zone valves in, let this thing speed up and down. You want to go after the Delta T style circulators, let that modulate as the season changes all winter long, right? So modulate as much as you can. All right, when that boiler went in, the warm and fuzzy brochure that was given to the homeowners, it showed on the front side of it, hey, 96% efficient. The big old cast iron behemoth that was there pulled out was around 78%. And now they're expecting to see, a good drop in their fuel bill. And they're not seeing it. They're seeing a small amount, but not as much as they are expecting. And that's because this thing is not modulating as much as it can. All right, it's not going as cold, it's not condensing. All right, so you want them to get to that 96. Hey, they invested in this new boiler. All right, give them everything that they're looking for by getting that water temperature as low as possible out to the delivery side. All right, now if you have a multi-temp system, meaning you do have a couple of heat emitters that do need higher temperature, when you do the math and all of a sudden you have a couple of them that need a lower temperature, there's no reason why you can't put mixing valves on it. All right, and putting in, say, a modulating mixing valve that has its own outdoor sensor and its own logic to modulate the water temperature to that lower temperature zone. Let the boiler do the high temp and let the mixing valve do the lower temp. All right, that's actually what I'm doing here. So yes, reset the reset, right? So yeah, when you start looking at it that way. So now we get more system reset rather than a boiler reset. Now you've got a system reset because you can see what's going on. So I have a high temperature radiant that my boiler does to an underfloor system at 145. My slab calls for 110, and then I have a 120 underfloor in my part of the house, right? So I got the 3 sections, 3 different water temperatures, but 2 mixing valves thrown in there to really bring that temperature down low as possible. So this boiler condenses all day long. So it's interesting when you take a look at the math and take a look at the numbers, not even just the math, the numbers after the fact. So my house that I'm in now is, yes, that in-laws house that I renovated, put the new boiler in 12 years ago. I bought that house 9 years ago, and we put an addition on, a 900 square foot apartment for the in-laws. On an 1,800 square foot house. So they got a 900 square foot apartment. They got their own kitchen. They got their own laundry room, everything running off of gas. 1 boiler doing both sides of the house with 2 kitchens, 2 laundry rooms, all the appliances are gas in the house. And we ended up with the exact same fuel bill, the exact same. Now, before it was fin tube baseboard, now I have radiant floor heating in the house. So I got the temperatures even lower. All right, got that temperature even lower. Like I said, it was doing 155 on a design day. Now I got it down to 145 on a design, and then 2-hour water temperatures out there to let this boiler condense as much as possible. Now, why else condense? Doesn't mean you can eliminate the service on the boiler, but at least you can, the boiler will operate a lot cleaner too when these things start condensing. All right, I have a fire tube condensing boiler, and my heat exchanger is a heck of a lot cleaner. And I remember on my first cleaning, yes, the shoemaker's shoe is never mended, right? So I got to my first cleaning on the boiler in about 2 years instead of that first year. It was 2 to 2.5 years by the time I went to go clean that heat exchanger. And I was talking to the manufacturer and a friend of mine there, and he says, "Oh, do me a favor as you take it apart, take a picture of the heat exchanger before and after you clean it." So, and my boiler sat up high like it does here in this picture here, and it was a little high up there, and took the cover off, got in there, and I had to reach down with the phone, take a picture, and I sent it over to him, and he looked at it and he goes, "All right, so where's the before shot?" I'm like, "Well, that is the before." He goes, "Really?" And I'm like, "Yeah, this thing is condensing all day long." All right, hooked up to a complete radiant system. So not that you shouldn't clean them, but hey, you know, you'll get it to last a heck of a lot longer. So with that being said, everybody, all right, like I said, I was running a little bit fast. I might have been talking too fast today. I finished actually a little bit early. So please type in any questions whatsoever that you may have, whether it's something that's on the screen, something that was 5 screens ago, whatever you have, I will stay on as long as possible, as long as you want me to today, on any questions that you may have on trying to lower the water temperature as much as possible. As we also start looking into the new world of our heat delivery system, not the delivery, but the BTU maker out there, not necessarily being a boiler, but as we start thinking about air to water heat pumps, all right, being able to deliver low water temperatures for us. They do get some very high temperatures too, you know, but what I mean by very high is about 140 degrees, right? So as we start looking at beneficial electrification is something to think about, is something to consider as we start thinking about air to water heat pumps being able to do all this stuff for you too. All right, so while you guys are all typing in any questions, if you have them, as you're hacking away on the keyboard itself, next week, Takeo Tuesday will continue, and next week will be the commercial focus. So June 28th is going to a deep dive into Takeo's SKV models. All right, so we'll be going a deep dive with Rich and Brett on that circulator pump designs. So make sure you tune in. If you haven't yet, you're going to get an email in 23 hours time with a link to today's presentation, so you can go ahead and watch it. But 2 will also be a link to register for next week's class. So for those of you that are still online with me today, I do want to say thank you for hanging out with us. I hope these have been educational and informative to everybody out there when it comes to the Takeo Tuesday series. We do enjoy, I mean, it seems like they were born out of necessity with COVID kicking in, but we've actually been doing webinars for over 10 years. We just started doing more of them as we went into lockdown way back when. So if there are any topics or ideas that you have, please do not hesitate to email us when you get that email next week, tomorrow, in regards to the recording and whatnot. Please send over any ideas. All right, they will be sent over to our marketing people that help set up these Takeo Tuesday classes, and they will pass those ideas along to us. So looking forward to the next couple of months of Takeo Tuesday class. I think I do have some already scheduled. I don't remember all the topics. We do have them listed if the topic has already been drawn up. So. All right, got a question from Kerry. Could you explain a little more on what the outdoor reset is doing? Yes, very good question there, right? So outdoor reset, when we start putting these boilers in for homeowners, we start talking in terms that we know, right? And what I want you to do is to not, because we start talking to them in lowering water temperature or sending a cooler temperature out to your heating, and like, wait a minute, cooler temperature? What do you mean cooler? What's going on here? Well, the best way to describe what outdoor reset is doing is use it in their terms like cruise control in a car. Why do we all use cruise control? It's not because my foot's tired. All right, cruise control is all about fuel economy. As hard as you might think that you're the best driver out there, that you can keep your foot on the gas pedal and not move it whatsoever, your foot is constantly going up and down, and you're adjusting it almost subconsciously nowadays, right? So, but cruise control is all about fuel economy. So I want you to paint the picture. Think about this for a second. You set cruise control for going 60 miles an hour, going across flat land, right? You're going nice and flat. Look at what's going on and listen. You hear the engine at a certain RPM. You can see the RPMs. You can hear the injectors, all right? And you stay steady at 60 miles an hour in your car, all right? This isn't your work truck or anything like that. Think of your car, all right, that you have. So now start going up a hill. As you start going up the hill, what happens to your speed? It should stay the same, right? It's going to stay the same. If it was a work truck, yeah, you're going to slow down because you got all that extra weight in that vehicle, right? But in your car, you're going to maintain that same speed. But as you look down, you're going to see the RPMs go up. You're going to hear the injector starting to work a little bit more. Now, so everything it's harder to drive up that hill. Hey, think of it this way. It's getting colder outside. As it gets colder out, I need to speed up a little bit. I need to speed up the mechanics on the inside and what's going on. Now we start going down the hill. You start heading down that hill, RPMs start to drop off, your injectors start to drop off. All right, we stay the same speed. Hey, it's getting warmer outside. I don't need as much anymore. All right, so I hope that helps you there in helping explain what outdoor reset is. So on your outdoor reset, what we're going to do is find that design water temperature that you need. All right, so for example, today we had a couple of different examples. Let's say it was 120 degrees. What is your outside design temperature? All right, if it was here on Long Island, it'd be 14 degrees. So we set up the curve on the boiler to give me 120 degree water temperature when it's 14 degrees outside. Boiler doesn't need to give me anything more than that. 120 degrees when it's 14. As it warms up outside, it doesn't send out 120 degrees anymore. It sends something that's less warm. And you can also program it to have a bottom end. All right, how cold do you want that water temperature to go, or how low? So a lot of times that curve is set up to go down to 70 to 70. So 70 degrees outside is 70 degree water. So you may not want that. You might want to goose that temperature up. If it was a radiant floor system, maybe go to 100, 95, 85, depends on your application for that water temperature. So you can program those numbers in there, and so it'll modulate between, say, that 120 and 85 degrees, depending upon how warm it is or how cold it is outside, but never going over, say, 120 degrees. All right, so I hope that makes sense to you, Carrie. Let's see, Ali asks, what are the other drawbacks using the lower water temperature other than radiator size would get bigger? Things take a little bit longer to heat up and cool down. All right, or heat up anyway, not necessarily cool down, but it takes things a little bit longer to heat up and respond to thermostat settings. That's it. That's really the only other thing that I find with low temperature hydronics. All right, and it's the understanding, like I said, explain beforehand. Afterwards, it's an excuse. So Vince is asking, north side location, an absolute must. My new installed direct vent combi will be approximately west to southwest side of the house. It will be a rather long run. Well, what's going to happen is that the sun is going to hit that sensor. And if the sun hits it, it's going to register a warmer temperature, which means it's not going to send out the cooler temperature that the house is actually going to need. So all of a sudden, it's not operating the way it's supposed to be. And like I said before, then the sensor gets disconnected, all right, and it just runs and doesn't modulate. So yeah, when the sun hits the sensor, it can raise the temperature or think it's 10 degrees warmer than it actually is outside. Think about it, right? I mean, right now where I am on Long Island, I think we're in the low 70s today. Go stand in the sun, feels nice and warm. Get underneath the tree. You get underneath the tree and it feels a lot colder, all right? But meanwhile, all you did is just take 10 steps forward to get in the shade, and it feels colder while you're there because you don't have that radiant energy. So that's what you need to consider when that sensor is not on the north side of the house. Make sure it's not getting in that direct sun load. Some people will try to put it underneath a deck. All right, it's in the shade, but the sun is still hitting the deck, and that air can get a little bit warmer down below too. So if you're not sure, there are several manufacturers that do wireless sensors. All right, and you may have to, $100 to $200 or so, and you can do a wireless sensor. If it's a 10K anyway, I've seen some of them out there that you can go wireless and get it to the north side instead of running that wire. So stop and think about that too. Spend the $100, or if it's going to be a really long wire, so what? All right, that's okay. I think you can easily run up to 150 feet of 18 2-stat wire is all you need. All right, not looking at anything special when it comes to that sensor wire that you have outside. All righty, excellent, everybody. Well, this was a great Takeout Tuesday again. I do greatly appreciate it. So we still have a handful of you out there. If there's any other questions, please type them on in there. Efficiency means using the coolest fluid to heat a home and the warmest fluid to cool a home. That's right, high temperature cooling and low temperature hydronics. Think about that for a second, right? all right, especially when we go into, looking at heat pumps and stuff like that, air to water heat pumps. You want high temperature cooling. Doesn't need to be down to that 42, 45 degree fluid. We could do something a little bit warmer, all right, and still cool a home. And I remember some of that from my old days back in my Radiant days. We were doing some radiant cooling applications and designs. So anyhow, excellent, everybody. Greatly appreciate seeing you all today. Well, actually, you see me. I didn't get to see you. I am starting to feel better, Eric. Thank you very much. That just means I'm stuck in the house for the next couple of days and have to isolate from the family. Like I said, I was supposed to be up in Rhode Island this week, and I was probably just going to steal away into an office to do the Takeo Tuesday class today. But we got some big meetings going on up there. So anyways, I'm starting to feel better. So thank you very much. Thanks, Steve. Eric, good to see you. All right, James, good to see you. 100%, hopefully soon enough. Yeah, I'm going to have to probably stay off the golf course this weekend too. Anyhow, thank you, everybody. Have a great day. Look forward to seeing you all again real soon. Enjoy.